Today, we're diving into the very fabric of sound. We're going to explore a completely new, kind of revolutionary way to see what it truly looks like.
So, take a second and picture a sound wave. You're probably thinking of that classic squiggly line, right? Wiggling up and down. But what if I told you that's only half the picture? That sound has this whole other dimension that, for the most part, we've just been completely ignoring.
Okay, look at this. On the left, that's the old way we'd visualize sound, a simple spectrogram. All it really shows us is amplitude, how loud it is. But on the right, that's the new way. This is a log complex color image. It's not just a line, it's a representation of the total sound. The difference is just, wow. So what's going on here? What's hiding inside all that color?
To really get what a huge leap this is, we've got to talk about the one crucial thing that those old black and white pictures were leaving out. And that missing ingredient? It's called phase. See, every sound wave doesn't just have loudness or amplitude. It also has a phase, which is basically its position in its cycle. And this little piece of data is packed with rich detail, information about where the sound came from, how it traveled. But most of our old visualizations, they literally just threw it away.
So, how do we get all that juicy information back into the picture? Well, it turns out we need a whole new recipe for seeing sound.
And this is it, log complex color. And the idea behind it is actually beautiful in its simplicity. It takes those two key parts of a sound wave and maps them onto every single pixel in an image. So amplitude, the loudness, that becomes how bright the pixel is. And phase, all that rich data we were missing, that becomes the pixel's hue, or its color.
So how's it work? Well, first, you capture the sound. Then, you use a really cool mathematical tool called a Fourier transform. Think of it like a prism that breaks the sound apart into all its individual frequencies. And from there, it's just that simple mapping process we talked about. Loudness becomes brightness, and phase becomes color. It's this incredibly elegant way to capture the entire sound in one image.
Now here's the part that just blows my mind. Because these images have all the original data, both amplitude and phase, they're not just pictures of the sound. In a very real way, they are the sound. You can actually take one of these images, run the process backward, and get the original audio back perfectly. Absolutely nothing is lost.
Okay, so we have these beautiful, complicated images. But what are we even looking at? Let's figure out how to actually read the language of these colors.
The secret is all in how the colors rotate. It's actually a pretty simple code. If you see the color cycling from red to green to blue, that tells you the frequency is a little bit sharp, a little above its center. But if they go from red to blue to green, that means the frequency is a little bit flat. It's a super simple visual cue for how well something is tuned.
So you know what that means? The easiest thing to spot is perfect pitch. If a sound is perfectly in tune, sitting exactly on its frequency, you'll just see a solid, constant band of color. No rotation, no shift, it means no misalignment. It's pure, stable pitch that you can see instantly.
All right, enough theory. What does the world actually look like when you see it this way? Let's take a look at some familiar sounds.
Okay, first up, an oboe and a clarinet, both playing the same scale. Now, even if you can't quite tell them apart by ear, their visual fingerprints are completely different. See those bright horizontal stripes? Those are the harmonics. And just look at how the patterns, the colors, they're totally unique to each instrument. They tell a different story.
And this table here really spells it out. For the oboe, that first harmonic, the one right above the main note, is super strong. But for the clarinet, it's actually the second harmonic that's the most pronounced. These are the kinds of tiny signatures that log complex color just makes pop right out. Now let's check out the human voice. This is just a simple woo, war, wow theater exercise. As you watch, you can see that main band of color shifting as the vowel sound changes. But look closer. See all those other, fainter bands of color up above? Those are all the rich harmonics that give a voice its unique texture. It's all just laid out for us to see. Even a sound as simple as a dripping faucet is hiding secrets. You might expect just a simple vertical line for each drip, right? But look at this. See those incredibly intricate, almost feathery bands of color that stretch out from each drop? That's all that hidden phase information, showing us a complexity you would just never hear.
And for the finale, let's look at a full orchestral piece. This is Anitra's Dance by Grieg, and it is just an absolute tapestry of light and color. You can see the sharp, bright lines from the violins, the softer tones from the woodwinds, the deep, rich colors from the bass. Every single instrument is weaving its own thread into this picture.
So clearly, this is way more than just a neat trick to make cool pictures. This technology opens up a whole world of real-world applications.
I mean, the possibilities are just huge. Imagine visual field guides where you could see the difference between two similar bird songs, or new tools to give the hearing impaired a much richer picture of the sounds around them. Think about musicians getting instant, perfect feedback on whether they're sharp or flat. You could even use it to analyze how a sound moved through space. It's wild.
And you know what the best part is? This isn't science fiction. The processing is so fast that it only takes about a third of the sound's actual time to create the image in real time, which means this technology is ready for the phone in your pocket
Today.
This really is a fundamental shift. Like the creators say, it lets us use our highly developed visual pattern recognition skills on audio data in a totally new way. For the very first time, we can really, truly use our eyes to make sense of the hidden world of sound. So we'll leave you with this thought to chew on. If every single sound, from a symphony orchestra to a drop of water, has this hidden visual fingerprint just waiting to be seen, what else about our world have we been missing?